Welcome to Evil Corp. I am Director Mercury of the Kidney Stone Production Laboratories. In this orientation video, you will learn everything you need to know in order to become an entry-level worker in the largest corporation on the planet. But first, you will need to have a brief history of this laboratory in which you will be joining. Our company began small. In the middle of the 1950s, after the first failure of the Evil Corp doom ray, the reason for its failure was found to be a lack in a certain substance known as calcium oxalate. This is where my slightly less evil clone and I found our calling. We discovered a revolutionary method of producing calcium oxalate inside the human body. These weaponizable lumps of calcium oxalate then became known as kidney stones. Of course, we had to study solubility extensively to discover this revolutionary method. So after we began our laboratory work, we then expanded, eventually dominating the market for solubility. Of course, then we had to keep expanding. So, since we already worked with some of the smallest equilibrium constants known to science, the obvious next step was to work with the largest equilibrium constants known to science. This then brought us to complex ions. 10 years later, 20 years ago, Kidney Stone Production Laboratories became the largest laboratory for solubility and complex ions in the world. I now turn this video over to my slightly less evil clone in order to teach you these concepts of solubility and complex ions. I am the slightly less evil clone of Director Mercury. I'll be teaching you about the two base concepts we work with here at the Kidney Stone Production Laboratories: solubility and complex ions. Both of these work in equilibriums, so they have their appropriate equilibrium constants that we mainly work with. With solubility, we have KSP. It represents the part of a precipitate that will dissolve back into solution. It's usually very, very small, as precipitates are, by definition, mostly insoluble. And they're based on the equilibrium format where the precipitate is the reactant and the derivative ions are the products. Because the precipitate is a solid, it can't factor in as a concentration. So KSP just equals the product of the concentrations of the ions involved. My example here is silver chloride, which is in equilibrium with silver and chloride ions. The KSP equals the product of silver and silver ions and the concentration of silver ions and the concentration of chlorine ions. Because they both have a coefficient of 1, they're both to the first power. The KSP for this is 1.8 times 10 to the negative 10th. As you can see, it's very small, since silver or chloride is insoluble. Okay. The equilibrium value we use for complex ions, on the other hand, is Kf, which stands for the constant of formation. It represents the tendency for a complex ion to form, usually very large, since complex ions tend to be fairly stable. They're written as in equilibrium form as the metal ion and the ligand as reactants and the complex ion as a product. Our example here is a complex ion made out of silver and ammonia. The Kf is then calculated with as the concentration of the complex ion over the product of the concentrations of silver ions and the square of the aqueous concentration of aqueous ammonia, since it has a coefficient of 2. This constant of formation is calculated to be 1.7 times 10 to the 7th. Silver chloride and silver ammonia are applicable beyond the theoretical because they are often used in identifying silver if it is in solution with other ions, or if we want to know if there is silver in a solution with other metal anions. While solubility equations can be adjusted like any other equilibrium with temperatures and the such, there are also two things that can also greatly affect solubility. One is pH, the other is the common ion effect. For this example, I'm using calcium carbonate, which dissociates into calcium and carbonate ions. Carbonate can act as a weak base, combining with hydronium ions to form water and the bicarbonate ion. So if we raise the pH of the solution, that will raise the concentration of the hydronium ions, and according to Le Chatelier's principle, shift this equilibrium towards the products. That will reduce the concentrations of the carbonate ion, which, again, according to Le Chatelier's principle, now that this side of the equilibrium is reduced, this equilibrium for the solubility will shift towards the products as well, causing calcium carbonate to become more soluble. pH, the common ion effect, does almost exactly what the name says it does. It involves another set of ions dissociating, one of which shares a common ion with, in this case, being calcium. Seeing as how we have calcium chloride here, which completely dissociates into calcium and chloride ions. Since the calcium ions are completely dissociating here, but only partially dissociating here, the calcium chloride will almost completely dissolve, while the calcium carbonate equilibrium will be shifted more towards the reactants, making it far less soluble. Now that we have covered the basics of solubility, we can go into the other side of our business here at the Kidney Stone Production Laboratories, and that is complex ions. Complex ion is formed when a metal cation and a ligand, which is either a molecule or an anion, linked by a coordinate covalent bond. The three most common ligands are hydroxide ions, ammonia, and cyanide ions. Since they have pairs of free electrons, that can be used for the coordinate covalent bond. For example, we had silver ammonia as an earlier example, and it forms coordinate covalent bonds with the two ammonia, since they have these free pairs of electrons. When I first introduced complex ions, I mentioned the equilibrium constant being Kf, constant formation. The problem with the constant formation, though, is that it's so big that we can't effectively use it. So instead, we have to use its inverse, the constant of dissociation, Kd. Kd is merely the inverse of Kf. So with our silver ammonia, which has its Kf, the KD for it would be if we instead assumed that the forward reaction went all the way to completion, and then our equilibrium had the product from our first reaction, the silver ammonia, as its reactant, and that it dissociates into the metal cation in the ligand. And this gives us an equilibrium constant small enough to work with. And now that we know how complex ions and solubility equilibriums work individually, now we can figure out how they work together. To do this, we have an example problem. And that is, what is the molar solubility of silver chloride in 1 molar ammonium? So, since it's an ammonium solution, the silver ions will react with ammonium to form a complex ion, in addition to the silver chloride dissociating into the silver ions and chloride ions. So, to solve this problem, we're going to need to put these two together to see how they work together. So, once we add the equations, the silver ions cancel, and when we multiply the equilibrium constants, we get our new constant, which is the complex ion multiplied by the concentration of chlorine ions all over the concentration of ammonia squared. Now that we have our K value, we can do a start-change equilibrium chart to calculate the molarity of the chloride ions at equilibrium. Once we solve for X, which is 0.050, we can plug that in for the equilibrium value of the chloride ions. And since the chloride ions and the silver chloride are at a 1-to-1 ratio, for the molar solubility, that means 0.050 moles per liter will dissolve into solution of silver chloride, right, per liter of solution. So the answer for the molar solubility is 0.050 molar. And now that we can figure out the solubility and how it changes individually, the complex ions and how it changes individually, and how solubility and complex ions affect each other, you now know the basic concepts you need for your work here at the kidney stone production laboratories. Now that you have learned everything you need to know to begin your work, all that is left in this orientation is a few notices from the Department of Human Resources. Casual Fridays are not lab coat optional. We wear them for a reason. We'd rather not hire more workers than we have to. The janitorial staff would like to remind you to please not blow up your labs overnight. There is no janitorial staff in the building between the hours of 2 a.m. and 7 a.m. So if your lab is blown up during this time, the soot stains will set and will make it much harder for your lab to become clean. The weekly downsizing is always on Thursday, though it may be on Friday. Choose your friends and allies carefully, as then you will know precisely where to stab them. I hope that we will have your valuable services with us, as long as they remain valuable, which will hopefully be for a long, long time. Welcome to Evil Corp.